Hi, my name is Peter Andras. I'm from Kiel University, and I will be talking about modeling the evolution of social institutions using composition of games. The talk first covers briefly social institutions, their evolution and modeling. Then I will be talking about games and the use of diagrams to represent games. Then we'll be moving to composition of diagrams and the use of this composition to make complex games. Then we will look at a couple of examples of such composed games and the complexity of games in relation with the level of cooperation in these games. And finally the talk is closed with my conclusions. So let's first look at social institutions. These really comprise a set of rules, norms, mechanisms, which are organized in certain patterns in society, and these really implement the ways how society works. So, for example, social institutions are involved quite often in allocation of resources, for example, deciding where to build an incinerator in a city or where to invest in shops. It is also quite often used for resolving conflicts. So, for example, which part of the city should be developed. And generally, these social institutions are used to channel the representation of interests of individuals and groups of individuals. So, for example, if you consider communal fishing, there are several groups which like to use the same fishing area, and they decide how to manage the representation of interest and how to resolve conflicts and how to allocate resources across the whole fishing population. Now, the question is how these social institutions evolve, because clearly at the beginning of society these were much simpler, and as society develops, more complex institutions develop in these societies. So really at the fundamental level it is about mutual help between individuals and ways of reaching mutual understanding. So for example, if you look at a parent and a child, how the child learns how to hunt, or if you look at a group of people who hunt together. So these are all examples of increasing complex social institutions. Now the question is how these relatively simple kinds of social institutions, like parent teaching a child or group hunting, evolve to much more complex social institutions like voting systems, political systems, large corporations. How does this evolution happen? Now, modeling social institutions has been around for a long time. If you look at various games, they quite often represent social situations. Consider, for example, chess, which is a kind of abstract way of waging war between two armies. Or consider other simple games like rock, paper, scissors game, where you have three different actions. One beats another one in a circular way. Or if you think of coalition formation in politics or elsewhere. Now, in all these cases, you can use games to model the social institutions. The question is, how do you use these abstract games to model social institutions and their development? So generally, so if you think of the rock paper scissors or prisoner dilemma, these capture relatively simple interactions. Perhaps more complex interactions are captured, for example, in chess or Go, where you can play strategies and those strategies can be analyzed. However, in these complex games, typically we have just two partners. So really the question that is not really resolved by current models is how do we get from these relatively simple games to the much more complex games which we can observe in today's society. Here what we propose is a new way of looking at games using diagrams. So what we propose is that all games are represented using diagrammatic blocks. These are the decision blocks, the aggregation blocks, splitting blocks, and impact blocks. Now, the decision blocks represent the decision made by participants. Aggregation block represent the transformation of a set of decisions into another set of decisions. The splitting blocks derive from one decision a number of other decisions. And finally, the impact blocks show how decisions have an impact on the participants. Now, always in the games we have a set of decision blocks at the start and a set of impact blocks at the end. And the aggregation and the splitting blocks in between are the transformations of decisions. In a sense, you can see this as similar to the rewriting rules. Now here you see a simple example, prisoner dilemma. So you have two participants who either cooperate or defect. One, depending on whether they cooperate or defect, they get some payoff. The R is the payoff for both deciding to cooperate. T is the payoff for one who decides to defect while the other cooperates. S is the payoff for a participant who cooperates and the other defects. And P is the payoff if both of them defect. Now, to represent this game using the proposed diagrams, you see it in the lower half of the page. You have the two participants, the decision blocks which generate their decision, then the aggregation block which transforms the decisions into the payoffs, and then the impact blocks which calculate the impact of each payoff on the two participants in this case. Where does this become useful? Well, we can compose these diagrams. So in particular, aggregation and splitting blocks with the appropriate inputs and outputs can be combined in novel ways. So this diagrammatic representation of games allows a quite intuitive combination of the splitting blocks and aggregation blocks to create new games. Now, whether a composition is meaningful or not can be determined by analyzing the inputs and outputs, and if necessary, additional inputs and outputs can be added to the composition to make the game, the composed game, meaningful. Now, let's see one example here. This is a three-player prisoner dilemma game where we have three participants. Each makes a decision using their decision blocks, and then the decisions generated by these decision blocks are used for three aggregation blocks which generate the prisoner dilemma payoffs. And then these payoffs are led into the impact blocks which calculate the impact on the three players. So what you see here is that essentially the prisoner dilemma diagram is composed. We have three blocks of prisoner dilemma actually played by three players. Each pair plays one prisoner dilemma, and this diagram representation allows a meaningful combination of these three prisoner dilemma games in an intuitive way. In this case, the final payoffs will be what are shown on the screen. Now, here you see another similar composition with a difference. Here again we have three players, they have their decision blocks, generate the decisions, then the aggregation block 1 is the aggregation block that applies the prisoner dilemma payoff calculations to these decisions, and then we have an aggregation block 2 which alters these initial decisions and generates a new payoff decision. Now, where that becomes important is that in many actual real social institutions, you have many layers of decision making, many transformations of the initial decisions, representations of intermediate decisions, and calculations of transformed decisions. Right? So this prisoner dilemma game combination or composition of three prisoner dilemma games plus these second aggregation blocks just captures this kind of more complex social institutional organization. Next to the image you see the final payoffs where these depends on a number of parameters as well. Now, let's consider one particular case. What this means in the three-player composed prisoner dilemma games, we have the final outcomes shown on the screen. And for the three-player composed prisoner game with decision transformation, we have the parameter shown on the screen, and you see what are the final outcome calculations. Now here, what the important to note is that in the second game, the outcomes are somewhat different from the outcomes in the first composed games. So, what we look at, it's a simple question: do we get more cooperation in the composed games? And here you see the results. So first is after a number of turns in a steady state of the simulation, where do we get? So here the simulation is a relatively basic simulation where you have a number of agents which move in a two-dimensional space, and the neighbors may decide to cooperate or defect in the games that they play. What you see is that the level of cooperation is much higher for the three-player game with the modified decision making than in the three-player game with combined, just plain combination, and both are well above the simple prisoner dilemma game. Interpretation of this is that social institutions of increasing complexity facilitate the increase of the level of cooperation at steady state level of these institutions. Similarly, on the other side of the screen, what you see is the relative population size. So this is how many times do we increase the population size compared to the initial population size as we get to the steady state simulation. And again, what you see is the same ordering. The largest relative population size is achieved for the combined and modified prisoner dilemma game with three players. Then we get somewhat less population size for the simple combined version, and much less for the plain prisoner dilemma. So again, our interpretation of this is that the relative size of populations grows with the complexity of the social institutions, at least in the context of this simulated society. Now finally, this result is interesting, which shows how is the relative resource amount, average resource amount across the population. Now here what you see is that the ordering is reversed. Most average resources are in the simple prisoner dilemma game, and as the social institution, the modern social institution gets more complex, the relative level of average resource amount is decreasing. Now, our interpretation of this is that actually this is just a reverse of the ordering by level of cooperation. More cheating means that there are individuals who are likely to accumulate more resources, while less cheating is a more egalitarian, leads to a more egalitarian system with a much less likelihood of individuals accumulating large volumes of resources. And so this, what we see here, is just the reverse of the cooperation level, and effectively what it implies is that if you reduce the cheating, then there will be fewer who have excessively high resource amounts. So to conclude, a novel conceptual framework is proposed here to model the evolution of social institutions using games, and in particular using this diagrammatic representational games, which allows the composition of them such that more complex games can be derived, which are meaningful games, using simpler games, and these can be seen as models of more complex social institutions. Finally, to note is that the two compositions of games that I presented are really kind of handcrafted compositions. In principle, automated composition of meaningful complete games is possible, because the methods that I described allows the automated checking of whether a composition is meaningful, and also allow the automated completion of composed games to make it meaningful. Thank you.